Welcome to All Things What. In this episode, we will be talking about time dilation. Time dilation shows up in Einstein's theory of special relativity, and it is really the difference in the elapsed time as measured by two clocks. So 1 hour elapsed on the first clock may be 2 hours on another clock. In simple terms, time could be moving faster or slower for one person as compared to another. Before I explain this further, we will need to visit one postulate of the theory, which is that the speed of light in vacuum is constant related to any observer, no matter what speed he may be traveling. So let's say we have a car that is traveling at 50 miles an hour, and we have a boy that is standing away from it, but the car is approaching it, and to alert the person, the car flashes its headlights. Now, what that means is the beam of light or a photon is emitted from the headlight all the way to the boy. We call the speed of light as we know it is c. So it being a constant, which is 3 raised to 10 raised to 10 raised to 8 meters per second in vacuum, we should note that the postulate states that the speed of light is constant, which is c, and not c plus the additional 50 miles per hour boost that it was getting because it's in the car. So that's a very important postulate, that the speed of light, no matter who the observer, is always constant. Okay, now that we have that said, let's get into the example of where we have another boy here that is sitting or standing, playing in the park. It's on the surface of the earth. What he observes is a plane and in the plane is a boy as well. Now our person here has superpower vision, that he can see into the plane, and he sees a boy who's playing a game, and that game is basically a very simple game. He takes a light flashlight and flashes the light straight above him where there is a mirror, and that mirror is d distance away. And what happens is the light just goes up, bounces off this mirror, comes back down, right? Pretty straightforward. But what the observer sees, the observer on the surface of the earth, or this boy who's in the park, is actually sees that the light travels, instead of straight up and down, travels in this trajectory. Now, we know from basic trigonometry that a right angle triangle, this being the hypotenuse, is the longer side in this triangle. So if this is d, this has to be something that's greater than d, right? And then the same thing applies here. If this is d, this has to be greater than d. Okay, so the person on Earth sees that the light travels this path, the dotted line, while the person that is in the plane just sees the light goes up and down, traveling a distance of d both one way. Now, another physics 101 formula is time is equal to distance by speed. So now let's calculate in both of these cases what this means. For the observer, I'll denote it with T of O being observer, is equal to the distance, which is something greater than 2d, so I just added these two up, divided by the speed of light, which here is c. Okay. And for the time for this person in the plane, we'll denote it with P for plane, is really 2D divided by C. Now note that C is constant, right? So this C here is the same as this C. How do I know that? Is because of this postulate that we have stated above. So now if these two C's are the same and this term is greater than this term, so that means T of 0 is greater than T of P. So what does this mean? Essentially what this means in real world time, let me tie it back, is the time elapsed for the person that is in the park, T of 0, is larger than what the time elapsed for the person who's in the plane. So to expand this further, essentially, the faster you go, right? So faster you go, time for you will elapse slower. So this has an interesting thought exercise to say, you know, what if I get on a fast spaceship and come back after a while? Will I have aged less or more? Right. So there's actually I won't get into this, but there are plenty of videos on twin paradox. I encourage you guys to go watch that. Where a twin sets off in a spaceship and travels a few years while the other twin actually sits back on Earth. And when the twin comes back, you essentially see that the person that is on Earth has aged more than the person who's been traveling, and this is only because he's been traveling fast. And as you theoretically, as you go closer to the speed of light, the time for you is passes extremely slow. In other words, you barely age. Okay. In fact, one practical example that we see about time dilation is that of GPS satellites, right? So if this is Earth, and let's say we have a satellite that rotates, actually revolves around Earth, and usually these GPS satellites are pretty fast, so they move at almost 4 to 5 kilometers per second, right? And what we'll end up doing is actually we need the accuracy of this, the atomic clock on here. We land up noticing that the time here does not sync with the time that's on Earth. In fact, the time here on the GPS satellite is elapsed less versus what it is elapsed on Earth, right? So this is always greater. And so every once in a while we need to go back and sync this up so that we are in the right time for precision. Okay, great. So this is all I had to talk about time dilation. I hope you guys enjoyed it. Stay tuned for more interesting topics on all things what.